Log on, tune in, find out. Another good idea from Cambridge.
So you might wonder why I'm here. Actually, there are special functions coming up in this talk, and there are discrete integrable systems coming up. So I have every reason to be here despite the title. Okay, so this work is mostly in collaboration with Leonia Chekhov, who is visiting now Loughborough on an EPSRC grant, and so I will give an introduction to Teichmuller spaces. I will give you the definition, and then if you're not happy with the definition, and I don't expect you to be, I will also show what they really are with my hands, and then I will show you how. So I will focus on. I will denote Riemann surfaces by the letter F. Sorry about this. This is somehow convention in the small community working in this area. And they will have three indices, one for the genus, one for the number of holes, so this is just chop away a little bit of the Riemann surface and make a hole, and one for the number of orbifour points on it, okay? So the three indices, and I will focus on especially two cases, one with no points and one with zero genus. They are somehow simpler. And then I will show you there is a natural link with the Garnier systems, and then hopefully I will show you how to get some Poisson algebras, which are infinite dimensional and are apparently new in the sense that we have shown them to many people and they don't seem to have seen them. And they seem to play quite an important role in several areas of mathematics, so it's quite nice. So, right, I will start with the definition of Teichmuller space. And so one of the most important objects in algebraic geometry is the moduli space of Riemann surfaces, yes? So you take a Riemann surface with a certain genus and a number of holes. Let me just deal with the compact case now. So just certain genus, and then you ask yourself how many there are with that same genus. What does it mean, how many? What is a Riemann surface? It's a complex manifold, so the question is how many atlases you can define, or in other words, how many complex structures you can put on a certain Riemann surface with a certain genus. And this is, so to speak, the moduli space. And you do that up to diffeomorphisms, which preserve the orientation, because if you consider orientation reversing diffeomorphisms, then you map the complex structure to its complex conjugate. Okay, so that's more or less the definition of moduli space. And this is a very difficult object to deal with. So we instead deal with the Teichmuller space, which is the covering of the moduli space. Namely, you take all distinct complex structures up to diffeomorphisms which are isotopic to the identity. So they're in the same connected component of the identity. Now, for the case in which you start abandoning the compactness, and you, thank you, and you you add holes and orbifour points, there is a better definition, which is based on the fact that the complex structure is in one-to-one correspondence with the metrics up to conformal the transformations, and in each of these classes, equivalence classes, there is a unique representative which has constant curvature. Okay, so you can define the moduli space as the constant curvature matrix you can put on a Riemann surface up to orientation preserving diffeomorphism, and the Teichmuller space is the same object up to diffeomorphisms isotopic to the identity. The relation between the two spaces is simply that the moduli space is the quotient of the Teichmuller space by the action of the so-called mapping class group. And one of the aims of this talk today is to give a good coordinatization of the Teichmuller space and describe the action of the mapping class group explicitly by an action of the braid group. And I'm going to focus on hyperbolic Riemann surfaces. I'm noticing that this is quite small. Can you read it? at the back? Yeah? No, because it looks small to me. So, well, anyway. So if this transparency has left you completely bored, as I can see on your faces, I have to give the definition, okay? So now I've given you the definition. I will go to show what the hell I'm talking about. Right. So let's take the first non-trivial case of Riemann surface of negative curvature. It's a Riemann surface of genus 2. And what are we doing? So we want to determine this surface. Yes? So what I do, I just choose 3 cycles, which are not homotopic to each other, and I chop. Take my scissors, and I chop it in pairs of pans. Yeah? So, yes. Sorry. This is a pair of pants because it becomes something like this, yeah? Okay. So I chop it in 2 pairs of pans, okay? And 2 of them. Now, each pair of pans is uniquely determined up to isometry by the length of its so-called belts, or however you want to call them. Okay, so once you know the length of those 3 geodesics, you know your pair of pans uniquely up to isometry, so you know everything about it. And now, how do I know the Riemann surface? I know it by specifying how I glue this pair of pans. So obviously, if I glue them with certain angle, I'm going to get a different Riemann surface than if I glue with a different angle, okay? So the Teichmuller space is the space of all these 6 coordinates in this case. The 3 geodesics lengths and the 3 angles by which you glue them. And you can generalize this to higher genus. It really takes 3 seconds. I haven't drawn it for you because drawing them takes longer. But you can prove pretty quickly that the dimension of Teichmuller space is 6G minus 6. And I specify that this dimension is real dimension because obviously they are geodesic lengths and angles, so they are real variable, okay? And this description generalizes to the case in which we allow holes. So let me just add 1 hole. So what is a hole? Is something we chop it off from the Riemann surface this way. And to coordinatize this thing, I have to add another pair of pans. Yeah? So now I have 3 pair of pans. There is 1 which is due to 1, 2, and the 3rd geodesic is the perimeter around the hole. Then I have this one, and then I have the one as before. Okay? And so, however, in this case, you see, I have no twist parameter there, and the length, the geodesic length is fixed. So adding 1 hole only adds two variables, right? So in general, so if S is the number of holes, I add 2S. And you can do the same with the points. In that case, you have a pair of pans in which you cannot put your foot through because you're going to, it's something like this. So this is point. Okay? So this is the object I'm dealing with, and yes. And then in this talk, I will give other coordinates in this space. These are the so-called Frenchel-Nielsen coordinate. And the next step is to replace these by other coordinates. And I will show you also another intuitive idea, I hope at least intuitive to me, why you can do that. So let's focus on the twists. Essentially what I'm going to do, so before we have 2 kinds of coordinates, geodesic lengths and angles. Now I want to get rid of the angles, okay? So to get rid of the angles, it's a very simple observation that suppose you are gluing in a straight way. So I just say this is phi equal to 0. The red geodesic is the geodesic along which I had originally cut my Riemann surface, and now I take another geodesic which is transversal to it, okay? The blue geodesic here. I chop and I glue in a different way. I glue by adding a small twist. What happens to the blue geodesic? Well, it gets deformed, okay? So obviously the length won't be the same anymore. So this is a very intuitive explanation why, in a sense, you can replace angles by some other geodesic lengths if you are clever. If you choose them in a clever way, you can replace the variable angles by other geodesic lengths. I'm not being very precise here because, in fact, choosing these geodesic lengths is not a trivial problem. But let's just accept the fact that we are going to give coordinates on the geodesic lengths only. If we can coordinatize the space of geodesic lengths, we are in business, okay? And then, yeah?
But it's very beautiful, so you're saying it's a change of variables. You can use angles or you can use lengths.
Yes.
And do we know, is it that it's not a linear change of variables?
No.
Is it an invertible? Does it have non-zero differentials everywhere?
I don't do it explicitly. So, in fact,
it's difficult.
Yes. So essentially, it's really philosophical at this stage. So I'm just trying to say
the number of parameters is
yes, the number of parameters is the same, and you can use geodesic lengths. However, as you are very right, I have no clue how to actually perform this change of variables. Okay, that's an absolutely honest statement. Yeah. However, yes, so there is some gain, however. Even if we are not able to say what the change of variable is, we can do an awful lot of things in these new coordinates. First of all, we can compute the Poisson brackets. So we can compute the Poisson brackets. So there is a result which is saying that the Teichmuller spaces are symplectic manifolds, and there is a symplectic structure on them which is called Weil-Patterson form. When you start reading about this, you realize that mostly this Weil-Patterson paper is an existence theorem. They don't really produce the Poisson bracket. So the nice thing about this is that if you decide to forget about the angles and do everything geodesic length, then you end up writing the Poisson brackets explicitly. And also, what I will show you is that you can write the action of the mapping class group explicitly again. Okay? So the main object of today are geodesic lengths on Riemann surfaces. All right. So, and in fact, I'm going to replace this object now by Fuchsian groups. So this is the second ingredient of the story, which is the fact that a Riemann surface with constant negative curvature can be seen as the quotient of the upper half plane by the action of a certain Fuchsian group. Fuchsian group is just simply a discretely generated subgroup of elements in PSL2R. Okay? So I think that if you did that hyperbolic geometry when you were little, you must have seen this, but I will remind it to you, because if you haven't worked on it for so many years, you must have forgotten. So I'm just making an example. In this case, I want to reconstruct my Riemann surface, which is in this case a torus with one hole, and I want to reconstruct it from a Fuchsian group. Okay? So in this case, I consider a Fuchsian group of two generators, gamma 1 and gamma 2. One generator is and I'm writing here the fundamental domain of this Fuchsian group. So the way you read this fundamental domain is that the two generators, one is the generator which identifies, for example, the bottom dashed geodesic with the top dashed geodesic, and the other generator is the generator which identifies the left green geodesic with the right green geodesic, okay? So we have two generators, and they act this way. So, and you really do the identification, right? So this is the upper half plane. I identify. So what it means, I really chop it out and glue it with super glue, the dashed lines, for example. When I do that, I'm just creating an infinite hyperboloid, like the middle figure, and in which I just copied the green geodesics there, okay? And now I do it again. I glue it again along the green geodesics, and I actually obtain, my Riemann surface there, okay? So this is what Poincare uniformization in a pictorial way is. Every Riemann surface of constant negative curvature can be realized in this way. So you can think of the Teichmuller space as the space of all possible Fuchsian groups, in a sense. And how do you, I told you before, I'm coordinatizing the Teichmuller space by geodesic lengths. What's the link with the elements in the Fuchsian group? The link is based on the following result, lemma. So, for every element in the Fuchsian group, we have an invariant axis. So you see, if I consider the element which identifies the dashed geodesics, the red axis is invariant. It's not moved by the action of that element. And when I go through my identification, I discover that that becomes a closed geodesic in my Riemann surface. And the same thing for the element which identifies the green geodesics. I see that there is an axis which is invariant, and that corresponds also to a closed geodesic in the Riemann surface. And in fact, the relationship between the element, the matrix in the Fuchsian group, and the length of that closed geodesic is very simple. So the trace of gamma of the generating element in the Fuchsian group is 2 cos of the length of the geodesic, okay? So we have a very, very simple relation. And so now we see that coordinatizing by geodesic lengths may be the same as coordinatizing by traces of matrices. It's going away. Okay, so please, I'll just repeat this because otherwise I'm going to lose you. In the next slide. So what I've done so far, I show you that each Riemann surface, giving a Riemann surface is the same as giving a group of matrices in PSL2C, R, sorry. And giving geodesic length is the same as taking traces of elements, okay? So these are now my coordinates. And now the trick. So, trick, the beauty of this story. This is, in fact, a program, a long-term program, which we have realized only in 2 special cases, but we expect it to work in general. And so the program is the following. I've lost it again. Okay. First of all, we interpret the Fuchsian group as monodromic group of a certain Fuchsian system. Why? Because it's me, that's what I do as a job, finding Fuchsian systems everywhere. So, right. Then we use a result by Korotkin and St. Leben to map the Poisson bracket, which is defined on the matrices of the Fuchsian system, to a Poisson bracket on the monodromy matrices. Damn it. Okay. So this I will explain. It's not that this is just a program. And then so this is a bracket. In fact, this bracket is not Poissonian. It's a bracket and doesn't satisfy the Jacobi identity. However, when you restrict this bracket to adjoint invariant objects, such as traces, it is Poisson. So we can deduce the Poisson algebra on the traces of elements. And this gives the explicit realization of the so-called Weil-Patterson form on the Teichmuller space. And then the most interesting fact is that we then start clashing poles in the Fuchsian system. And then repeating the procedure, we find new Poisson algebras on the result. Okay, so that's what I'm going to realize today in a very specific case. So this is the program in general, and we are fairly confident that it's going to work. However, for the moment, it only works for a very specific case, which is a Riemann surface of G0, so sphere, with one hole and n orbit 4 points. So this is an object which looks like well, a sphere with a hole. And then it has some points on it. Or topologically, you can think of a disk with points. Okay. Now, so in this case, the dimension of the Teichmuller space is 2 times n minus 2. Now, when I saw this, I got completely excited, obviously, because I knew this number very well. It's the dimension of the Garnier system, right? It's the Garnier system with n plus 1 poles, so n finite poles and 1 at infinity, as the symplectic manifold has dimension 2n minus 2. And in fact, that's what happens. So our matrices are 2 by 2. Nothing easier than that. You just take the Fuchsian group and say, okay, I associate to it a Fuchsian system, Fuchsian group, Fuchsian system, I mean, cannot be wrong, right? And and then you say, okay, I associate this Fuchsian system and I study this Fuchsian system. In particular, I will show to you that in this specific case, these monodromy matrices are traceless. And if, as a consequence, in the Fuchsian system, all the eigenvalues of the matrices are plus or minus 1/4. And then the matrix at infinity is generally diagonal, and the diagonal elements depend on the length of the geodesic around the hole. Okay? So, and I hope we all know that the isomonodromic deformations of this system are given by the Schlesinger equations, and which reduce to the Garnier system. So this is very nice. Okay, so how to use this? A little bit. This is a result by Korotkin and St. Leben. Then you can establish the so-called Riemann-Hilbert correspondence, which associates solutions of the Schlesinger equations to monodromy matrices. On the space of solutions of the Schlesinger equations, you have the standard Lie Poisson bracket on LSMC, I mean, the standard linear Poisson bracket. And essentially what Korotkin and St. Leben did was to transfer this bracket to the space of monodromy matrices. In particular, you can formulate the Poisson bracket on SLMC in R matrix formulation, which is very cute. And so as a commutator there, with R is just some constant matrix over lambda. And so let me call this matrix omega. Then that omega is transferred to the Poisson bracket on the monodromy matrices. So the formula is very explicit. And I keep calling it Poisson bracket, but it's not. It doesn't satisfy the Jacobi identity. However, it's a very beautiful bracket. And it does restrict to a Poisson bracket once you look at what happens between adjoint invariant objects. So if I take trace Mi or trace Mi mk and look at the Poisson bracket with another trace, then it is in fact satisfying the Jacobi. Right.
Is there an intuitive way to understand why the Riemann-Hilbert correspondence doesn't preserve the Jacobi?
Intuitive way to understand.
Well,
I mean, if you're already lucky that it actually works, you know.
Yeah.
I think the main.
But I mean, if you just thought of this as you made a smooth map between the A's and the M's.
It has to be more than smooth, right? If you want to preserve it. Poisson bracket. It has to be a symplectomorphism, and it has to be. So
Or it's not.
I think something breaks down at a certain stage. I haven't looked honestly into detail why. No, so I don't know the answer to your question. Right, so I'm just using this formula. I mean, the way you prove it is a bit technical. So you have to choose a basis of loops, and then you look at the solution of the Fuchsian system, so the solution of your Riemann-Hilbert problem, and you start deducing. So this is written as a certain integral in a clever way, and then you start deducing a bracket between psi and ak. Then you deduce a bracket between psi at a certain point and psi at another point, and then by quite extensive computation you find the bracket between the monodromy matrices. So I haven't looked in detail where the Jacobi breaks down, but I know that if I just take this formula and try, it's not working, yeah? Okay, right. So let me let's take this formula and consider the following objects. Gij is the trace of two elements in the Fuchsian group, of the product of two elements in the Fuchsian group, okay? Gamma I times gamma j. Gij is defined in that way. And then you start applying the Korotkin-Santleben bracket, and you find that it gives you this very beautiful formula, which is due to Ugaglia in 1999. And as you can see, it's a closed Poisson algebra in the sense that the right-hand side is only a combination of traces of product of two matrices, okay? So you don't need to add anything more. And so this is, in fact, the semi-classical limit of Nelson-Regge algebra, which appears in quantum gravity, and there are several reasons why that is true, but I won't consider these reasons here. And there is another theorem by Chekhov which says consider instead another set of geodesics. These are, let me see, geodesics which join two points on your Riemann surface, two of the orbifour points on your Riemann surface. Then, by placing Gij equal to the trace of these two guys, I get the same algebra. Okay? And in fact, so what I'm going to show you in the next few slides is how to choose a basis in the Fuchsian group such that, in fact, it is true that gamma ij is gamma I times gamma j, and how you get this theorem here. It requires quite a lot of machinery, but I hope I can lead you through it. It's a little bit, so please stop me if I am a bit, sorry. Right, no, before doing the machinery, because the machinery is going to make you sleep, right? So I give the machinery at the end. I first give the results, right? So now what do we do? We start clashing poles. So what I consider is a Fuchsian, it's a Fuchsian system now with n plus m poles, okay? I just decide to call the number of poles n plus m. And then I decide to clash, sorry, that should be an m. I decide to clash the last m poles, okay? The way you do it from an analytic point of view is simply saying that un plus j is equal to, for example, t, some new pole u0j, and then send t to 0. Okay, it's very simple, and you can write the Schlesinger equations in T, and this was in fact done by Jimbo and Miwa, and they studied the clashing. So what they do is they take the limit as t goes to 0, and what they find is that you get a new Fuchsian system, by the way. So if you do things very, very well, you're not getting irregular points. You keep Fuchsianity, which is really amazing. Okay, so and this new Fuchsian system has n poles, which were the ones of before, the first n, which we didn't touch, plus the new pole, which is created by clashing all these, okay, all these ones. So these I call U0. Then there is also a beautiful link between the resulting residue matrices and the AKs. It's, you know, there is algebraic dependence. So AK as a function of the clashing parameter T is simply an algebraic function. It's beautiful, algebraic asymptotic. So all these AK0, B0, everything is under control really, really nicely. And the new monodromy matrices, so now I get a new Fuchsian system. These has n plus 1 finite poles and 1 at infinity. And the new monodromy matrices are the first n monodromy matrices of the original system and one new monodromy matrix, which is the product of the previous last m monodromy matrices. Okay? It's a very simple picture if you think about it. You know, you can consider your let's take a base point and consider a basis of loops. 1. Okay. And then I have the other ones, un plus 1, sorry, and so on. If I clash, for example, these two, the picture is simply replaced by this, yeah? That's the topological reason why that's happening. So the new matrix is simply the product of those.
Sorry, Marta. Why do you get simple poles by clashing?
It's because, well, there is a very technical condition which I'm hiding under the carpet, and which is about. So the answer is this: that if you have a beautiful dependence somehow of AK on T asymptotically, then you can guarantee that that happens. And the way you prove that, in fact, this is the case is by some technical condition on the eigenvalues of this matrix B0. Now, it's it's a very beautiful result by Jimbo Miwa, which maybe we can talk about later because it's fairly technical. I mean, to be able to have Fuchsianity, as I say, you have to be really careful. And so I don't think I can do this now, otherwise. Okay, so now we have now I need to be a little bit careful because somehow I've created a new object, and somehow this new Fuchsian system remembers that it's coming from a clashing. So I need to introduce new elements. So I call the old element Gij with the 0 here. So it's simply the trace of gamma I times gamma j. And then I have some elements which I call Gij which are the traces of gamma I times gamma 0 to the k, gamma j, gamma 0 to the minus k. And this is a little bit mysterious, but I will tell you later why. And then I start doing the Korotkin-Santleben bracket. So, and this is the result. I know it's not very pretty. So let me just lead you through the result. Okay, so the Poisson algebra is the algebra for Gij for all I, j, and k's. So I and j run from 1 to n, but k belongs to z. Okay. And so if I take the Poisson bracket between, say, an element with a q there and an element with 0, that's fine. The right-hand side only depends on traces with 0 and q. So that's good, it's closed. However, when I start having both elements with non-zero, we call it level, like for example in this expression, you see I take the Gij1 and the GKL1, I start generating G with 2. So I cannot close this bracket, you see, because at every step I'm going forward with one element. And in fact, normally when I take the bracket between level M and level K, I find level K plus M. And so everything gets mixed up. And so the Poisson bracket is really not finite. The interesting thing, though, is that suppose we now forget what these Gij are. So I don't want to consider the fact that they are traces of some products of matrices. Let's just treat them as abstract objects, okay? This is still a Poisson bracket. So this satisfies Jacobi, satisfies all the definition of the Poisson bracket, which is really amazing, because if you look at it, yeah, it's quite striking, I think. And it can be formulated, you see, it's not even homogeneous because we have K minus M here, so it's a little bit. So we've been looking around quite a lot with Chekhov to try and see if somebody had found this object already, and it appears it's completely new. Is not, I mean, I don't know if there's experts in the audience on Yangians. It's certainly not a Yangian, is not a Kac-Moody, is a new animal, okay? So in the next 10 minutes, I'm going, no, less, 5 minutes, which is, I'm going to kill you with the machinery, but at least I want to show you how things work, possibly, okay? So what's the machinery? Okay, so sorry, this is what I was saying. So we have an infinite dimensional abstract Poisson algebra. Actually, it doesn't depend on how many points we clash. When we consider it as an abstract algebra and forget about the origin, we don't see the origin anymore. And what essentially describes geometrically is that when I'm clashing, so when I'm clashing a few points, what happens is that these points form a new whole from a geometric perspective. So we have constructed the Poisson algebra of the geodesic length instead of a sphere with marked points on a cylinder. Okay, so we have two holes. So to prove all this, I need machinery, and the machinery is the following: is the so-called fat graph technique. So again, I will make the easier example of the torus with one hole. And what you do to construct a fat graph. What is a fat graph? It's a graph which is trivalent, and each face must contain exactly one hole. So there are several ways. This is in fact quite a misleading picture, but it's quite intuitive too, so I will do it anyway. So you, for example, on the Riemann surface, you select a bouquet of cycles. They intersect in the wrong way, because it's a 4-valent intersection. You split the intersection, and then you make it fat, and that's your fat graph. The real way in which you do it is completely different. You take a Riemann surface, you triangulate it in a clever way, and then you take the dual graph to the triangulation. But what I'm talking about is this, yes? So I just, for example, so you triangulate it in some way, and what is the dual is the graph which goes that way, yes? However, I did say in a clever way, and that clever way would require me a couple of hours of lecture to explain how, so I'm not going to do that. All right, so next step is to label the edges of this fat graph. So this is the same picture, just rearranged in a nicer, more symmetric format. And each edge is, what is it? It's a leg of the graph which goes from one vertex to the other. So in this case, we have 3 edges. I labeled them by Z0, Z1, and Z2. Now, each geodesic, or each generator in the Fuchsian group, what is it? Is a closed loop in the Riemann surface. Closed loops in the Riemann surface become closed loops in the fat graph. And what you do is you follow the fat graph, and you follow the loop in the fat graph, and you take notice of which edges you go through. For example, let me take this example. Let's decide to go clockwise. We go along Z1, so I write Z1. Then here at the vertex I turn right, so I write R. Then I go along Z0, so I write Z0. And then here to glue I go left. Okay? And the same thing here. I can write this curve as this 4-letter word. And now there is the brilliant idea by Fock, which says, well, loops are elements of the Fuchsian group matrices, so they are matrices. So these words are simply a way to decompose, factorize my matrix. And so he introduces some matrices of right rotation, left rotation, and edge matrix, and then he writes this Fuchsian element as a product, ordered product. So we first have an edge matrix, then T1 denotes either right or left, then another edge, then another right or left, and so on. And then in this way, he can coordinatize the Fuchsian groups by the labels which we appended to the fat graph. And notice that we actually only need to know which edges our geodesic go through. We don't need to specify if we turn right or left, because if I want to go from Z1 to Z2, the only way is to turn right. So we don't need that information. We just need to know for this one, I just need to know this is the geodesic which goes through Z1 and Z0. That's it. I don't need any more information. And in fact, you see that the matrix is specified by only Z1 and Z0. So, and you can prove that, in fact, in this case, you have that in a fat graph there are 6G minus 6 plus 3S edges, and this is the dimension of the Teichmuller space times the R to the number of holes. But this is not a problem, because in fact you can prove that they satisfy S relations. So for every hole, the perimeter around the hole is a given constant. So that's the relation. And so this is the dimension of Teichmuller space. You just proved that these are good coordinates on the Teichmuller space. So then the Poisson bracket on these coordinates is as easy as it can get. So let me perhaps draw yet another picture. So the convention is this, that edges can have non-zero Poisson bracket only if they meet at the vertex. Then you look at the vertex and you choose an orientation, for example, counterclockwise. No, actually I've oriented everything clockwise this talk, so let's do it clockwise. So you decide that if this guy is called Zi, then this is Zi plus 1, and the Poisson bracket between them is that one. And if this guy is Z1, then this is Zi minus 1, and the Poisson bracket is the minus of that. Okay? It's quite simple. And what they find is that this is actually a result by Chekhov and Penner. I'm sorry I haven't written this here. Is that this leads to the Goldman bracket between geodesic length functions. So this is a representation of it. What I mean by this is this. We take, so this is maybe actually not very useful today, so maybe I can skip it. So, but anyway. So it's saying that the Poisson bracket between the length of the red geodesic and the length of the blue geodesic is 1/2 the length of this geodesic, which is obtained going along gamma twiddle first, so the red one first, and then along the blue one, minus 1/2 of the one I get by going along the red one, and then the inverse of the blue. So it's a very explicit formula, and once you start, so this is really computational. It's very simple to compute, well, quite simple. And this is the way they proved that they had. So this is the way you get, sorry, perhaps I should go back here. This is the way you can prove that these are the Poisson brackets among the geodesics which go between the ith orbit point and the jth orbit point. Okay, now next. Adapting these coordinates to the case in which we have orbit points. In this case, the fat graph is slightly different. You see, when you have these points, you have a fat graph which has pending vertices. So it's not closed, and you have some vertices in the fat graph. The only difference is that you have to add an extra matrix, which is an inversion matrix F. The decomposition is exactly the same as before. However, here, you remember before I had edge matrix either and then followed by R or L. Now the edge matrix is followed by R, L, or F. So we have 3 options instead of 2, but the decomposition is precisely the same. And everything works beautifully again. And so now what I'm going to do is to show you the Fuchsian group. So I'm showing you the Fuchsian group, which corresponds to this face with several points, not only 3. And so as you can see, it's all very explicit. So you have edge matrix R, edge matrix F, edge matrix left. So it's really explicit. This is the picture of the Fuchsian group. Now, if you forget about the fat graph behind it, this is the normal picture you have here on the blackboard when you are doing your Fuchsian system. So this is why the idea came out. And in particular, you cannot see, but you see all of these matrices have F in the middle. On the right, I have a matrix, and on the left, I have its inverse. So they all traceless. It's very so. In this way, we can prove that, in fact, this is the Fuchsian, the monodromic group of a Fuchsian system of very specific kind. And we can prove that the simple geodesics joining the points I and j are given by gamma I times gamma j. Actually, this is evident from this picture, because if I take the product of this times this, well, this gives me exactly the curve which does that, right? I mean, it's quite simple, hopefully. Right, and then, oops, yes, and now let's, and then, so you prove all your results in this way, and now what happens when we clash the poles? Okay, so let me clash these two. Well, this is again quite simple pictorially. So the 2 poles clash into a hole, and the fat graph changes. So we have an extra hole, but the whole machinery works, and that's how you obtain your Poisson algebra. So now I have no time, so I will just say that then next step is the action of the mapping class group, and this is beautifully described by an action of the braid group, which is also a very beautiful result, because essentially what this result is saying is that the action of the mapping class group corresponds to the action of analytic continuation of the solutions of your Garnier system associated to your Teichmuller space. So I will stop on this. Thank you.
You start from some 1 or 2 object points in the surface, and there are
All V4 points.
all points. How about so many object points?
Yes, so that's the next step up, right? Because of course I can clash as many as I like.
So
I can divide my
divide
yes,
up.
and the clash here, clash there. However, there are some technical problems with that. As Andy was pointing out, Frank was pointing out, how can you guarantee that you're still sitting on a Fuchsian system? So as I say, that is a very fine analysis, and at the moment, I don't know, I haven't managed yet to prove that you preserve the fact that when you clash clusters, say, that more than one cluster, that you are still on a Fuchsian system. So this is the first problem. The second problem is also computationally quite exhausting, also from the point of view of the algebra, because then really already, but I think that's a technicality in a sense. I think that the main problem is, as Frank was pointing out, to prove that you're still in the Fuchsians. And you really need that. You really need it because I hadn't a chance to talk about this, but if I do want to describe the action of the mapping class group in the case in which I produce the holes in this way, the only way to do it is to be able to say that there is this correspondence with the Fuchsian system and I'm doing analytic continuation. So then I can say, yes, I can produce the action of the Drake group, but if I lose that information, I lose control. Yeah, I cannot prove it anymore.
And second question, so your system is so rank 2 system, or can you generalize it from genius to genius to higher rank?
No, for the moment it's 2 by 2, and the reason why it's 2 by 2 is because you are taking a Fuchsian group, subgroup of PSL2R.
You can read the subgroup of the PS2R.
Yes, so there are a lot of questions about compactification of Teichmuller space and considering solid Riemann surfaces and so on, but this is very, very far away at the moment. So on this level, the 2 by 2 is really very relevant to the construction.
Thank you.
If you carry on flashing poles, you can increase the number of poles. I mean, that's
Yes,
the way
that's
to
what
carry
was
on.
his
That's
point, yeah.
And then, but then, how about sort of actually make the genus one?
That's not actually.
Is that easy?
Yeah, well, easy, no, never.
No.
It's easier. It's
Then-
easier. So, yes, yes. In a sense, we have two very clear pictures. One is Riemann surface of any genus with holes and no orbifold point, and the other one is the sphere with hole and orbifold point. And the reason why we kept them separated is mostly computational. So I am confident that if I spend sweat and blood, it will come up with a higher genus. That's not a problem. It's increasing the number of holes might be more difficult, actually.
Isomonodromy. What are the systems that will come out? I mean, on the genus one, I can sort of analyze it, but
Okay, so you really want to know everything, don't you?
There is some experimental work on some deformations from the isometric deformation of F theta to the ES0.
yeah.
There are some experimental work.
Okay.
In this, I haven't said actually quite a lot of things, but and which also answers partially Oyama's question. And in fact, there is a relation with Frobenius manifold theory. Namely, I can consider these gamma ij's as elements in the Stokes matrix there. So now we're talking about higher dimension, and so you can obtain higher dimensional Fuchsian systems. However, the map is not yet completely clear to me, so that's work in progress to understand this correspondence. In a sense, I think this algebra which we found is very important in that area, because what you're doing is, in the Frobenius manifold theory, you're writing the Poisson algebra on the non-semi-simple points. So that's quite new. However, I at the moment I haven't really worked out all details, so that's work in progress, and I just.
To answer the question I had, you said at the beginning that this new Poisson algebras have applications.
Yes.
Is
So.
this the application that you
Yes.
envisage?
Yes, I mean, so let me just quickly go back. So the original, so this one is in fact the Poisson algebra on the Stokes matrices associated with the Frobenius manifold. Massive, so-called massive Frobenius manifold. What it means is that you take a Frobenius manifold, and the algebra which is on the tangent of the manifold is semi-simple. Okay, so in the semi-simple case, this is the algebra you find. Excuse me?
When you add this gamma 0 to the k.
So when you add the gamma 0 to the k, what you're really doing is you are looking at the Poisson algebra on the Stokes matrices of a non-semi-simple case. And to see this, well, is Laplace transform. To see this is Laplace transform, and what you find out is that, okay, so there is an isomonodromic problem associated with the Frobenius manifold in which you have it's irregular, right? You have a diagonal matrix. So it's this form, dy over dz, equal to u1 un plus, v over z y. And these are the same as the Fuchsian system's poles. So when I'm clashing them, what I'm doing is I'm saying, say that I have u0 here. And this is exactly, in fact, those are the coordinates of the Frobenius manifold. So what you're saying is that the algebra is no longer semi-simple. So that's, but okay, this is work in progress really, and we again with Chekhov, and I don't think we are going to finish before Christmas 2012. No. So maybe next workshop, I don't know.
Anyway, I guess we have all earned our coffee, so thank you.
Thank you for your attention.